Okay, let's talk about Albert Einstein's famous equation. Let me propose something here. Uh, let's suppose that you're in a rocket in deep space, and this rocket could be pushed ever so slightly in a straight line every day, all day long. And after many, many, many years, what would be your final energy of your rocket? That's what I'd like to know. And what would be your final velocity? Not to mention, we won't see you anymore. But let's say you're sitting in this rocket, you're all alone, and you're sitting in this rocket, you're absolutely motionless. And for some methods I've developed that I can nudge your rocket. I'm here on Earth, and some method I've developed that I can nudge your rocket forward every day, continuously, accelerated just slightly, ever so slightly. I can accelerate your rocket forward with a forward motion, and I do this every day for many, many, many years, if that's what it takes. And after a certain point in time, you're going to be traveling very fast, okay? And what I want to know is, I want to calculate, is what will be your final energy of your rocket and how fast you will be traveling. Okay, so let's get started. That's what I want to do. Okay, so essentially what I'm going to be doing is I'm going to be doing work on your rocket. Okay, and the equation for work is equal to force times some distance x. Okay, so I'm going to do work on your rocket. And once I do work on your rocket, then I'm gonna come along and I'm gonna change that work. Okay, I'm gonna say changing work is equal to force times the change in distance. Okay, or displacement. I'm sorry, displacement. So that's what I'm gonna do, and I want to use this equation. Let me make a little bit thinner ink here, and so dx. Change that. See if I got that. No. Let me get a thinner ink. Yeah, I'll do that. Okay. Is equal to displacement. I haven't gotten the thinner ink yet. Okay. Okay. dx is equal to displacement. Okay. Okay, according to Isaac Newton in the 1600s, Isaac Newton said that, and here's our equation. Let me rewrite it again. I can't seem to find my thinner ink pen. There's our equation. According to Isaac Newton said force is equal to the change in momentum divided by time, or with respect to time. Okay? And so, if I rewrite that equation, according to Isaac Newton, I would have the change in work would equal to dp, change in momentum, respect to time, times dx. Okay. And while I'm doing work on your rocket, what I'm essentially doing is I'm changing the energy of your rocket. So I can write that as dE is equal to dP, change in momentum, times dx over dt. And dx over dt is a velocity. So essentially I have the change in work energy is equal to velocity times the change in momentum, according to Isaac Newton. Okay. Now, according to Isaac Newton also, momentum is equal to your rest mass times your velocity. And so if I wanted to find the change in your momentum, I would take the derivative of the momentum was to be equal to your momentum, rest mass, times the change in velocity, plus your velocity times the change in your rest mass, okay, according to Isaac Newton. But according to Albert Einstein, in around 1905, Albert Einstein said that when you're traveling at high speeds, your rest mass has to be multiplied by gamma. And so he called that relative momentum. So we call this relative momentum is equal to gamma times your rest mass times your velocity. And gamma is equal to 1 divided by the square root of 1 minus v squared over c squared, okay? Okay, so if we rewrite this equation according to Albert Einstein, then what we would do is we would take the momentum, PR, relative momentum, and we would write it as relative mass, because now we call this gamma times the rest mass, relative mass, times your velocity. And if we would take the derivative of that relative momentum, okay, it would be equal to your relative mass times the change in your velocity plus your velocity times the change in your relative mass. Okay, so now our new dE, change in energy, would be equal to velocity times the change in momentum relative. Okay. Okay, so now let's take this equation, this new equation here, and work with it. And let's move down a little. Let me see if I can move this down some. And see what we got here. So we got, essentially, according to Albert Einstein, we have a new equation here. Okay. We have relative momentum is equal to your relative mass times your change in velocity plus your velocity times the change in your relative mass. Okay. So therefore, dE, our change in energy, is equal to our velocity times the change in our relative momentum. Okay. So I just take the relative momentum and plug it into here and multiply by the velocity. Let me get my pointer back. And so I multiply it through here, put dP in here and say V times relative mass times the change in velocity plus V times V is V squared times the change in the relative mass. Okay, and relative mass, as I said before, is equal to gamma times M. Okay, M naught. And gamma is equal to the square root of, well, it's gamma is equal to 1 over the square root, so let me correct that. Okay, so I corrected that now. Let me get my pen back. And so, and I draw a line down here, and I got that big pen. I'll get rid of that again. So now, so the relative mass is equal to gamma times M naught. M naught is known as your initial mass. Okay. And gamma is 1 over the square root of 1 minus V squared divided by C squared. Therefore, relative mass is equal to your initial mass, m naught, divided by the square root of 1 minus v squared over c squared. Okay, so let's take our equation here, right? This one right here in red. And what we got to do is we have to determine what this change in relative mass is, okay? And this is our relative mass equation right here. So we have to determine what the change in that is, okay? So let me take this equation and rewrite it. Because if I rewrite it, I can handle it much better. So I have the relative mass, and I'll call that mr, is equal to m naught times 1 minus v squared divided by c squared raised to the power of 1/2. Okay, that's the same as the square root, 1 over the square root. Okay, for those of you who don't know. For those of you who know algebra, you'll realize that's what that is. Okay, so let's take the derivative of mr. So the derivative of our relative mass, mr, is equal to minus 1/2 times m naught times 1 minus v squared over c squared raised to the power of minus 3/2. Okay. And then I take the derivative, what's inside of there, is equal to 2 times the volume divided by velocity times c squared times dv. Okay. So now let me rewrite this. I'm multiplying by 2, so the 2's cancel, and so I have dmr, my relative mass, is equal to, and I multiply by v, so I have m naught times v. The 2's cancel my 2's, and I'm multiplying by c squared, and so that's c squared times 1 minus v squared over c squared raised to the power of minus 3/2 dv. Okay, that's my equation that I'm ending up with right there. Okay. Okay, and this is a minus 2 here, so I missed that. But that's the change in what's inside of this parentheses is minus 2v divided by c squared. So therefore, minus 2 times a minus 1/2, the 2's cancel, okay? And so I multiply by c squared, and I end up with the rest mass times the velocity divided by c squared times 1 minus v squared over c squared raised to the power of minus 3/2 times dv. Okay? And when you're doing these calculations, I'm telling you, you have to be very focused on minus signs and your terms, because you'll lose them, especially when you're trying to make a video, okay? So bear with me here. And I have notes I'm looking at. I did these calculations, but I'm trying to make a video. It's very difficult to do this and keep track of this stuff and make a video. And every time I make a video, I mess up somewhere and I have to put a note on it or go back and correct it. So let me continue on here. What I want to do is I want to rewrite this term here, okay? And the reason why I want to rewrite it is because I can handle it much better in mathematically if I rewrite it. So let me rewrite. The change in relative mass is equal to m naught times v over c squared times, and watch what I do here. I'm going to rewrite this. 1 minus v squared over c squared raised to the power of minus 1/2. I'm going to change that to minus 1/2, and then I'm going to rewrite this again. V squared over c squared to a minus 1 power in dv. Okay. Now, what I want to do is I want to rewrite this again, and when I rewrite these, I I'm doing it so I can make these equations more easy to handle. Okay, so I have change in relative mass is equal to V over C squared, put a parentheses around that, times M naught divided by, well, this term raised to the minus 1/2 is just the square root of 1 minus V squared over C squared, okay? And this term raised to the minus 1 is really 1 divided by 1 minus V squared over C squared, okay? And that's dV, okay? So, and this term here, M naught over the square root of 1 minus V squared divided by C squared, that's equal to this equation right here. So I can rewrite this equation again and call this the change in MR, my relative mass, is equal to relative mass times V divided by C squared times 1 or dV divided by 1 minus V squared divided by C squared, okay? Okay. Now, I want to rewrite this again. And this time, let me rewrite it over here. Change in relative mass is equal to relative mass times velocity divided by C squared times dV divided by, I don't want to write the 1 there. I want to write this as C squared divided by C squared minus V squared divided by C squared, okay, dV. And put my dV over here also. Oh, I did put it on, okay. I did put it here, okay. I put it inside. So, okay. C squared over C squared minus V squared over C squared, well, since they both have the same denominator, I can add them. So change in relative mass is equal to relative mass times V divided by C squared times dV divided by C squared minus V squared divided by C squared, okay? And then that's equal to relative mass times V divided by C squared, and I can invert and multiply this now, C squared divided by C squared minus V squared, okay? And that's equal to times dV, okay, times my change in velocity. So these C squares cancel, okay? So now I can rewrite this equation as change in relative mass is equal to mr, my relative mass times velocity, divided by c squared, and since the c's cancel, minus v squared, okay, and dv, okay, and that's my equation that I end up with, okay. So now I can rewrite this equation, my equation here. I can rewrite. Let me get my pen back. The change in relative mass is equal to relative mass times the velocity divided by c squared minus v squared times dv, right there, okay, and that's our equation, okay. Let me get my thickness back here, okay. So what I want to do is I want to get back to I want to solve this equation and put dm relative, okay. but it's kind of difficult. It's going to be difficult if I plug it in like that. So let's take dm relative times c squared minus v squared is equal to mass relative times velocity dv, okay, divided by c squared minus v squared, and multiply c squared minus v squared. Okay, these cancel. Okay, so that leaves me with d derivative of relative mass times c squared minus v squared is equal to relative mass times velocity times the change in velocity. Okay, and then I multiply it through by this. That gives me change in relative mass times c squared minus change in relative mass times v squared is equal to relative mass times v times dv. Okay, and vdv, change in relative mass vdv, is located right here. Okay, so I just take this part right here and plug into that equation. Okay, and substitute it for that. Okay, so that will be the change in energy is equal to, plug this in, change in relative mass times c squared minus change in relative mass times v squared. Okay, then I have plus v squared dm plus v squared dm relative. Okay, and that's the equation I want right there. Now you'll notice that in this equation we have change in relative mass minus change in relative mass v times velocity squared plus change in plus velocity squared times change in relative mass. So we can, these cancel, these two cancel. Okay, so my final equation is change in energy is equal to change in relative mass times c squared. So I got to plug in change in relative mass again. Well, there it is right here. Okay, we used it before, so all I have to do is plug that in there. So the change in energy is equal to the relative mass times velocity times the change in velocity divided by c squared minus v squared, and all of that is times c squared. Okay, and that is my equation that I have to integrate. So what I want to do is now I want to rewrite this equation a little bit better than what it is, so it can be handled a little bit more. It'll be more manageable. So I'll rewrite this as change in energy is equal to c squared times the integral, and this is also, I'm going to integrate this from e equals 0 to e equals 1, and I'm going to integrate that from 0 to v of change of the relative mass times v dv over c squared minus v squared. Okay, and I just rewrote this equation here so I can deal with it. So now remember, the relative mass is equal to m naught divided by the square root of 1 minus v squared over c squared. Okay, so I can plug that in there. Okay, and to integrate dE from E0 to E1, that comes up to be E1 minus E0, which is equal to, I'm going to call it delta E. Okay, so that's equal to c squared times the integral from 0 to v of m naught divided by the square root of 1 minus v squared over c squared times times v dv over c squared minus v squared, okay, divided by c squared minus v squared. Okay, I can pull m naught out of there because that rest mass is constant. So I call that delta E is equal to rest mass times speed of light squared from the integral times the integral 0 to v of v dv divided by 1 plus v, 1 minus, I'm sorry, 1 minus, that's minus 1 minus v squared over c squared, and that's times c squared minus v squared. Okay. All right, there's the equation. Okay, so a few things I want to bring to your attention here. Notice that Einstein's famous equation has appeared. Rest mass, mass times the speed of light squared. Okay, so now what I want to do is I want to rewrite this and make this equation a little more manageable. Is equal to m naught times c squared from 0 to v, v dv, and I'm going to write this equation as, this is, I'm sorry here, I left my square root sign off there. So that's equal to 1 minus v squared over c squared raised to the power of 1/2 times c squared, I want to factor c squared out of there, times 1 minus v squared over c squared. Okay, so what I did was I factored a c squared out of here. Okay, so if I bring this c squared out here and cancel it there, these c squareds cancel there and there. So, okay, so now let me move this screen down some. And let's rewrite this again. So let me get my pen back here. So change in energy, and let me get rid of this thickness. I don't know why this changes like that. Change in energy is equal to m naught, okay, times the integral from 0 to v of v dv divided by, and this is a 1 here, so when I multiply this term times this term, that comes out to be 1 minus v squared over c squared raised to the power of 3/2. Okay, and that's the equation I have to integrate. Okay, and it's a little more manageable than it was before, because when you write it out like this, it makes it a little more manageable. But I still have to have some issues with this, because this equation is difficult to integrate. Okay, so what I'm going to have to do is make some assumptions here. I'm going to let u equal 1 minus v squared over c squared. Okay, this part, and then I'm going to let du is equal to minus 2v over c squared dv. Now I have dv here and I have dv here, so I'm going to solve for dv. So dv is equal to c squared divided by minus 2v du. Okay, so what I'm going to do is I'm going to take dv and substitute it into there. Okay, So I'm going to say the change in E, energy, is equal to m naught from 0 to V of V D. Oh, let me get rid of that. I'm sorry. Get rid of that. And I'm plugging into substituting for dV here. So that's going to be equal to times c squared over minus 2v du over u raised to the power of 3/2. Okay? And what's going to happen here is this v cancels this v. Okay? And so what I'm going to end up with is delta E is equal to m naught c squared, and from the integral from 0 to v, well, it's really from 0 to u, but I'm going to leave it like that, times u raised to the power minus 3/2 du. Okay? Now, this integral is easy to solve because this integral, the answer to this integral is, let me write it out. Change in energy is equal to m naught times c squared. And to integrate this, you just add 1 to the numerator, to the power, and divide by the result. So that's 1 minus 3/2 is u to the minus 1/2 divided by minus 1/2. Okay? And I pull out the minus 2 here, so my minus 2 is here. Oh, I forgot that. Minus 2. Okay? And I pull out my minus 2 here. So, therefore, minus 2 divided by 1/2 is 1. Okay? So, therefore, my the integral is equal to mc m naught times c squared times u raised to the power minus 1/2 okay, integrated from 0 to v. Okay. Well, what is u? Well, u was 1 minus v squared over c squared. So change in energy is equal to m naught times c squared times, and all of that is times that, 1 minus v squared over c squared, and that's raised to the power of minus 1/2. And I'll integrate that from 0 to v. Okay? Okay. So this is the final change out here. So change energy E is equal to m naught times c squared, and all of that's multiplied by from 0 to v. So that's 1 over the square root of 1 minus v squared c squared. Okay. Minus this term evaluated at 0. Well, when v is 0, c squared into 0 is 0, so that's the square root of 1. So that comes out to be equal to just 1. Okay. And so this is my final energy equation. And if I multiply it through by m naught times c squared, and let me get some room here. I'll get that to be equal to the change in energy is equal to m naught times c squared divided by the square root of 1 minus v squared over c squared minus times 1 is c squared, m naught times c squared. And this term here is your kinetic energy. Okay? And this term here is your rest energy. And this is Albert Einstein's equation. And this is Albert Einstein's famous equation. This is your kinetic energy, and this is your rest energy. Okay? And I included in here Albert Einstein's original equation I found on the internet. And there's what he had, how he derived it, and he said it equal to what he said it was: mass times the speed of light squared times this factor. And you can read what he said in his text here. Thus, when V equals C, W becomes infinite, which is the energy. He called the energy W. Velocity is greater than that of light have, as in our previous results, no possibility of existence. This expression for the kinetic energy must also, by virtue of the argument stated above, apply to ponderable masses as well. And as you can see, I included here a location for this document on the internet where you can go get it if you choose to read what Albert Einstein did. He didn't make that calculation like I did. He did it some other way, but I did it from the work done. So work done equals changes in kinetic energy, and so that's the way I did it. Okay, I hope that you enjoyed that, and I hope you learned something. Thank you.